All right, guys. So 3 out of 4 of these boundary conditions have been verified, and we need to verify this last one, that the concentration at the interface is in fact equal. So we will plug in for our piecewise function here a y sub I in each of these profiles, and hopefully they're going to be equal. Then we can have confidence in these functions that we derived, and then we can verify that it matches what we calculated with the resistance network. So let's start doing this. We'll plug in, I think again, these are going to get pretty large pretty fast. We'll plug in a y sub I, so this first expression is going to be Ca naught plus 1 times this ratio of diffusivities times the original concentration over this denominator that we've had. So on the left-hand side, Ca naught plus y over yi is 1 because we have yi over yi. Ratio of diffusivities all over, just this portion, over 1 minus h over yi minus this diffusivity ratio. And so this will be equal to, if we plug in a y sub I down here, let's just plug in the y sub I and rewrite this for now. We'll write CAO times y sub I minus h over y sub I. This is all over 1 minus h over y sub I minus this ratio. All right, so hopefully these things are equal. I think in a couple of steps here we'll be able to show this. So the first thing we can do is, if we get this over a common denominator, then we can just eliminate the denominator and focus on the numerator here. So to do that, we'll need to multiply this by 1 so we don't change the equality here. So it'll have to be this denominator in both the numerator and denominator. So we'll have this times Ca naught, then plus Ca naught times that. This is all going to be over this denominator that's equal to this function, and we're going to let those denominators cancel. That was the whole goal here. So this is equal to Ca naught And if we distribute this, we're going to have Ca naught minus Ca naught h over yi. Then we'll have minus Ca naught times this ratio plus Ca naught times this ratio. That's going to cancel, so that's all we have. And if we distribute this, we get Ca naught times yi minus yi is 1 minus Ca naught times h over yi. All right, and we do see that the left and right hand side are equal. So finally, we can go back and verify all 4 boundary conditions work. So hopefully now we plug in to our functions here and verify that the flux through either one of these materials, because it's equal, through the Pyrex and the silicon dioxide. We're at steady state. We have no generation. We have equal flux through this system. So we can solve either of these for the first derivative and multiplied by the diffusion coefficient, right? Using Fick's law, what we need to do is say that the flux of A, of helium in this case, is equal to negative the diffusion coefficient. So whichever material we choose, it'll be that diffusivity, times the slope. So each of these has its own slope, and what we need to do is take the first derivative of either of these functions, and we can figure out, does this molar flux match what we got with the resistance network? And I'll leave that to you guys. So what I would like you to do is verify that you plug in the same values that you were given in the exam, and you do get that same molar flux. And the other thing that we can verify is this. We can use the resistance network to find the concentration at Y sub I, at the interface. It'll be very quick and easy to do with the resistance network. And then we can also calculate the concentration at Y sub I. We just proved that they were equal. For either of these materials, we'll figure out what the concentration is, or I want you to figure out what the concentration is, and then we can talk about this during our next lecture.